Hello viewers, welcome to ChemSpawn Zone. So this video is in continuation with the previous video where I was discussing about nucleophilic substitution reactions of alkyl halides. So till now we have learned that these reactions are of two types, Sn1 and Sn2. So in the previous one we have learned about the examples of Sn2 reactions, mechanism and the factors that affect Sn2 reactions. Here I will be dealing with the Sn1 reactions. So before going to the today's content, so let me revise some important points of Sn2 reactions. So what we have studied that a general nucleophilic substitution reactions of alkyl halide can be represented by the reaction. Here in this type of reactions we can see that a nucleophile, which is a electron rich species, substitutes the halo group in alkyl halide, that is the substrate, and the halo group leaves as the halide and the nucleophile gets substituted in the product. So this is a general reaction of nucleophilic substitution reaction. So what is Sn2? In Sn2 reactions we can find that the nucleophilic substitution reactions in which the rate of the reaction is dependent on the concentration of both the alkyl halide and the nucleophile, both raised to the power 1. That's why this type of reactions are known as bimolecular. 1 plus 1 is equal to 2. If we increase or decrease the concentration of either the alkyl halide or the nucleophile, the rate is going to change. So next thing we have learned that what is the order of reactivity of alkyl halides towards Sn2 reaction. So we have learned that primary alkyl halide has highest reactivity for Sn2 reaction, followed by secondary and tertiary. We have learned the reason also. You can refer my previous video. I'll be giving a link in the description of this video. So we have also learned that the mechanism of Sn2 reaction involves only how many steps? Only one step. But it proceeds through a transition state. One step but proceeds through a transition state. Then we have also learned that Sn2 reactions are favored by polar aprotic solvents. Polar aprotic. This means these solvents are polar but they are aprotic. Aprotic means they are not able to provide proton in the solution, or they are not able to form hydrogen bond with the solute that are dissolved in these type of solvents. For example, DMF, dimethylformamide, dimethyl sulfoxides are the example of polar aprotic solvents. They do not provide proton, as well as they are not able to form hydrogen bond with the solute that is dissolved in this type of solvents. Coming to the nature of the leaving group, we have learned that what type of alkyl halide are preferred. We have seen that alkyl iodides have greater reactivity towards Sn2 than alkyl bromide, than alkyl chloride, than alkyl fluoride. I have told that primary alkyl halides have higher reactivity towards Sn2. So let me take example. Here I have drawn all the alkyl halides are primary in nature, but they differ in the type of the halo group. So you can see I have drawn the structure of alkyl ethyl iodide, then ethyl bromide, then ethyl chloride, then ethyl fluoride. All are primary alkyl halide. All will have reactivity affinity for Sn2 reaction, but which one will be having higher reactivity for Sn2 among them? They differ in the type of the halo group. The answer is ethyl iodide, because it has iodo group, and iodo group is a better leaving group. And if we see the reaction, ultimately the halo group has to leave. If the halo group is a better leaving group, the reaction will be faster. That's why primary alkyl iodide have higher reactivity towards Sn2. Next one is the inversion in configuration. That means whatever the product we get by Sn2 reaction, here I have drawn a reaction for Sn2 reaction. Primary alkyl halide with sodium hydroxide gives us the substituted product, and the halo group is leaving as the halide. That means chloro group is leaving as chloride. This is the primary alkyl halide. Ethyl chloride is giving us ethanol. Here we can see that the configuration of the configuration of the alkyl halide, the chloro group was facing right hand side, while in case of the product, the whatever the nucleophile is getting substituted, the hydroxy group was the nucleophile. It is in the left hand side, it is facing left hand side, so the configuration are opposite. Means configuration of the alkyl halide and configuration of the substituted product are opposite. That's why this type of reaction proceeds with inversion in configuration. So dear viewers, so these are the important points we have to remember when we go for Sn2 reactions. So let us come to our today's topic, that is unimolecular nucleophilic substitution reaction or Sn1 reaction. So what is Sn1 reaction? What is the difference with Sn2 is that the rate of Sn1 reaction depends on the concentration of only the alkyl halide. So here you can see that the concentration of nucleophile is not mentioned. Only the concentration, if we change the concentration of the alkyl halide, we increase or decrease, the rate is going to change. But if we change the concentration of the nucleophile, the rate is not going to get affected. Here only the alkyl halide has role, concentration of the alkyl halide has role in the rate of the reaction, and it is raised to the power 1. That's why it is called as unimolecular nucleophilic substitution reactions. So let us come for the order of reactivity of alkyl halides towards Sn1 reaction. In the previous one we can see that the order of reactivity was primary greater than secondary greater than tertiary. Here it will be opposite. So tertiary alkyl halide has higher reactivity towards Sn1 than secondary than primary. So why it is, we will understand when we study the mechanism. So this point I am going to discuss in the factors that affects the Sn1 reaction. So first, let us first take an example of Sn1 reaction. So I told that it is tertiary alkyl halide shows, or it has higher reactivity towards Sn1 reaction. So I am taking the example of a tertiary alkyl halide. This is tertiary butyl chloride. So in this case it is tertiary because the carbon that is bonded to the chloro group, it is directly bonded to 3 other carbon atoms. So when I am going to go for the reaction with sodium hydroxide, we can find that we will get a product. The name of the product is tertiary butanol, and the halo group will be leaving as the halide. That means it was a chloro group, that's why it will be leaving as chloride. So this is the example of a Sn1 reaction. Here now we'll be going for the mechanism of the reaction. We'll go for the mechanism, how it occurs. We can find a difference with Sn2. Sn2 was occurring in only one step, but it was proceeding through a transition state. Only one step, but proceeds through a transition state, that is Sn2. But in case of Sn1 we can find 2 steps. So what happens, let us see. So let us see what happens in step 1. In the step 1 there is a formation of carbo-cation. So how the carbo-cation is going to form, let us see. So let us take the tertiary butyl chloride. That tertiary butyl chloride will undergo cleavage Cleavage means the bond between the carbon and the chloro group is going to break. This breakage is heterolytic bond fission. Heterolytic bond fission means unequal bond breaking. So what happens here? Let us see. So chloro group with one covalent bond has already 3 lone pair. So what will happen? This bond is going to break. This bond has 2 electrons and those 2 electrons are shared between carbon and the chloro group. As the chloro group is more electronegative when compared to the carbon, the shared electrons will be nearer to the chloro group. These are the shared electrons. 2 electrons will be nearer to chloro group. That's why it will develop a slight or partial negative charge and the carbon will develop partial positive charge. Now when it will undergo breaking, what will happen? Both the electrons will permanently come to the chloro group. As a result, we will get a structure carbon with the 3 alkyl groups. Here all groups are methyl groups and the carbon will develop a positive charge because it has lost the shared pair of electrons and the shared pair of electrons have come with the chloro group. It was having 3 lone pair, now it will be having 4 lone pair. So this is the leaving group. So we have seen that we have got the leaving group in the first step itself and the alkyl halide has broken and it has given a carbo-cation. Carbo-cation means carbon with a positive charge. Now one more thing we have to notice that the structure of the alkyl halide was tetrahedral. If a carbon is tetrahedral, we know that the hybridization state is what? sp3. Now in step 1, this alkyl halide has converted into a carbo-cation and the carbo-cation has trigonal planar geometry. So tetrahedral shape has been converted into trigonal planar. Trigonal planar means in this geometry that this is a carbon and this carbon is attached to 3 other carbons and all these 4 carbons are in a single plane. They touches the same plane. So that's why it is trigonal planar. A carbon which has trigonal planar geometry, it is sp2 hybridase. Remember this point. I'll come to this point again. So next one, what happens in step 2? Till now the nucleophile is not involved. Only the alkyl halide is involved in the first step. Now what will happen? You see, we have the carbo-cation. Now the nucleophile is going to come. So what was the nucleophile here? I was taking sodium hydroxide. That sodium hydroxide is going to dissociate to give sodium cation and hydroxide ion. Now this hydroxide ion is the nucleophile here. Now the hydroxide ion is going to come and how it is going to attack, let us see. It has 2 options. 2 options means it can attack the carbo-cation. This is negatively charged, this is positively charged. Definitely it is having, both are having affinity towards each other. It has 2 options. It can either attack in this direction or in this direction. So you will be very clear if I go for the molecular structure. I told that the carbo-cation has trigonal planar geometry. Trigonal planar geometry. What is the molecular structure? Let us see for this carbo-cation. The carbo-cation which is sp2 hybridized, it has 3 sp3 hybrid orbitals. Sorry, which is sp2 hybridized, it has 3 sp2 hybrid orbitals. sp2 hybrid carbon, hybridized carbon has 3 sp2 hybrid orbitals with an bond angle of 120 degree. Now this sp2 hybridized carbon is bonded to 3 other carbons. The 3 other carbons are bonded by sp2 hybrid orbitals. Now we know that if a carbon is sp2 hybridized, it has one unhybridized p orbital. If this p orbital is vacant means there is no electron, then it is represented by the positive charge. So you can understand this positive charge is due to the vacancy of the unhybridized p orbital, or there is no electron in the unhybridized p orbital. This is the actual structure of the carbo-cation. This carbo-cation is a molecular structure. So what will happen when I take a nucleophile? It has two options. It can either come through the upper lobe of the p orbital, or it can come along the lower lobe of the p orbital, because this unhybridized p orbital has two lobes, upper lobe and lower lobe, and the nucleophile can go for the carbo-cation through the upper lobe of the unhybridized p orbital or through the lower lobe of the unhybridized p orbital. So here I am showing like that, in this direction or in this direction. So let us see what will happen when it comes in this direction. So we'll get that carbon, again the geometry will convert into tetrahedral geometry. The hydroxide group is coming in this direction, right? And if it attacks from this direction, what will get? C, CH3, 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 then OH. There is no difference. Structurally they have no difference. Molecular formula are same, but what is the difference? Configurational difference. So let us compare with the alkyl halide. Here the chloro group was facing right hand side. Here the hydroxy group is also facing right hand side. That means the configuration are same. That's why this is called as retention. Retention means the configuration of the product is same with the alkyl halide. And this here what you can see, the new hydroxy group is facing left hand side, while the chloro group in the alkyl halide was facing right hand side, opposite configuration. That's why it is called as inversion. So this is a very important point. So we can see that Sn1 reaction proceeds with retention in configuration as well as inversion in configuration. So we have two different options for the product when I consider the configuration. But in case of Sn2, we had only inversion in configuration. Hopefully you have understood till now. So let us go for the factors. The first factor is that order of reactivity of alkyl halides. I told that tertiary alkyl halides have higher reactivity because tertiary alkyl halides gives a carbo-cation which is tertiary, right? Why it is tertiary? The carbon having the positive charge is bonded to three other carbons. This is tertiary carbo-cation. That means tertiary alkyl halide gives tertiary carbo-cation, and we know that tertiary carbo-cation is the most stable carbo-cation. So you can have an idea that if the carbo-cation which is forming in the first step is stable, then only the first step can occur easily. If the carbo-cation that is forming is less stable, then this first step will be difficult. For example, I will tell, if I take a primary alkyl halide, this is ethyl chloride, and if I go for Sn1, step 1, what will happen? This bond will dissociate and I will get a carbo-cation that is primary, right? What is primary? Carbon with a positive charge is only bonded to only one carbon atom. On the other side we have hydrogen. This is less stable. This is primary, this is less stable when compared to the tertiary. So if I take a secondary alkyl halide, what will be the option? If it undergoes Sn1 reaction, then I'll get a carbo-cation which is secondary in nature, right? So this has intermediate stability, higher than primary, lesser than tertiary. Why? Let us see the reason. This can be explained by +I effect. +I effect means the groups which have the ability to push shared pair of electrons towards carbon are plus I groups. We know that alkyl groups are plus I groups. Here I can see that there are how many alkyl groups in tertiary carbocation? 3 alkyl groups. So they are plus I groups. They will push the shared pair of electrons towards the carbon. So carbon is getting this positively charged carbon is getting density from electron density from 3 sides. As electrons are coming from all the possible directions, the positivity will be stabilized to a great extent. The electron density from 3 sides are decreasing the positivity and making it stable. But if we see the primary carbocation electron density only from one side, here in secondary carbocation only from 2 sides. So this is the reason tertiary carbocation is the highest stable carbocation, then secondary carbocation, then tertiary carbocation. So therefore we can tell that tertiary carbocation will show Sn1 reactions with higher reactivity because they will give a carbocation which is the most stable. Got it? So this is the order: tertiary alkyl halide greater than secondary alkyl halide, then primary alkyl. This is the order of reactivity. Let us go for the next point. This is the nature of the solvent. So what type of solvent we have to prefer? The solvents should be polar protic solvents. Polar protic solvents are favors the Sn1 reaction. So we have to understand what is polar protic solvent. Now easiest example is water, right? So we know that water is a polar molecule. Why it is polar? So water has 2 OH bonds. Oxygen is more electronegative than the hydrogen. So the shared pair of electrons will be near to the oxygen. So oxygen will develop partial negative charge and the hydrogen will develop partial positive charge because the shared pair of electrons are away from it. So for this bond also the H will develop partial positive charge. So for this bond the direction of polarity is in this direction. For this bond the direction of polarity is in this direction, right? So if we take the resultant of these two, there is a resultant direction, right? If there is a resultant direction in polarity exists in a molecule, the molecule is a polar molecule, right? And what is protic? The solvent has the ability to donate to provide proton or to form hydrogen bond. So I have told that polar protic solvents favors Sn1 reactions. Why? So if I carry out this reaction in presence of water, how it is going to help? Let us see. So if I take the tertiary alkyl halide, right, this bond is polar, delta minus, delta plus. So in presence of water, delta minus, delta plus, delta minus, delta plus. So if I dissolve in water, what will happen? There is a possibility of formation of a bond, special bond between the partially positively charged hydrogen of the water and partially negatively charged chloro group of the alkyl halide. This type of bond is known as hydrogen bond. And how it helps, right? If I take water as the solvent, the water will form hydrogen bond with the partially negatively charged chloro group of the alkyl halide. When this bond forms between water and the chloro group, the cleavage of this bond becomes easier, right? And our motto is what? Our motto is to break this bond, isn't it? In the first step. So presence of polar protic solvent helps in the breakage of the CCl bond. So there are many examples like CH3OH, methanol, ethanol, then you can take acetic acid. These are the example of polar protic solvents. One more question you can ask me. These are the examples. Sorry, it may not be visible now. It is clear. I think methanol, ethanol, acetic acid. These are also the examples of polar protic solvents. So you can also ask me, sir, which solvent will be better for Sn1 among these 4? The answer is we have to consider dielectric constant. dielectric constant. Whichever the solvent, polar protic solvent, is having higher dielectric constant will be most favorable. For example, water is having around 78.5, dielectric constant is 78.5. Methanol is having around 33. Ethanol is having 24.3. So among these three, which is having higher dielectric constant? Water. If the solvent with higher dielectric constant can easily break this bond because they will be having higher affinity for the formation of the hydrogen bond. Is it clear? So very simple that polar protic solvents are favorable, and the polar protic solvent with higher dielectric constant will be better for Sn1 reactions. Coming to the next one, there is the nature of the leaving group. So it was like the Sn2, whatever the order I have shown. Alkyl iodide are preferred over, will be having higher reactivity over alkyl bromide, then alkyl chloride, then alkyl fluoride. Now I told that tertiary alkyl halides have better affinity for, or they have higher reactivity for Sn1. So if I take all tertiary, let me tell that this is tertiary alkyl iodide, tertiary alkyl bromide, tertiary alkyl chloride, tertiary alkyl fluoride, or tertiary. But what is the difference? The halo group are different. So which one will be preferring Sn1 most? The answer is tertiary alkyl iodide, because iodo group is a better leaving group and it can leave easily as iodide when compared to the bromo group, chloro group, then followed by fluoro group. So these are the three factors. That is the first one is your order of reactivity, tertiary greater than secondary than primary. Next one is your nature of the solvents, polar protic solvents, and the polar protic solvents with higher dielectric constant will be favoring most. Then we have to go for the nature of the leaving groups. Iodo group having alkyl halides will be having higher reactivity for Sn1. Then we have learned that the reaction has 2 steps and the rate is only dependent on the reaction of the alkyl halide. One more thing is that we can see that in the first step nucleophile is not involved, isn't it? Only the alkyl halide is involved. And when a reaction occurs in more than 2 steps, more than one step, that type of reactions are known as complex reactions. So Sn1 reactions are complex reaction because it occurs in 2 steps. And in the complex reactions, which the step which is slower or the slowest is known as the rate determining step. So among these 2 steps in Sn1, first step is the slower step among these 2. Therefore, for this complex reaction, Sn1 reaction, so this will be the rate determining step. That means this step will determine the rate of the overall reaction. And as in this step the nucleophile is not involved, only the alkyl halide is involved, therefore the rate of the overall reaction only depends on the concentration of the alkyl halide, not on the nucleophile. Thank you for watching the video. Hopefully you have learned about Sn1 and Sn2. In our next video I'll be coming up with the racemization in Sn1 reactions. If you have liked it, please subscribe my channel. Thank you for watching.